Okay, I'm going to cover booting. At least I'm not going to go through all the. So the CD-ROM boot sector goes on about block 16 hex. Anyway, my boot sectors, they reload. Okay, the BIOS loads the boot sector at 7C00. Mine copies itself. Mine identifies where it is. It calculates where it currently is, and it copies itself up to a location. Mine copies itself out of the way. Boot high location. Mine boot high location is up in the 90,000s. Okay, so my bootloader copies itself out of the way and uses the BIOS interrupt 42. I'm not messing with anything earlier than a 64-bit. All 64-bit computers have 1342. Where's 1342? 42 is the BIOS code. Interrupt 1342. So you're asking, how do I use absolute addresses? Well, let's look at my hard disk. That's the one I want to look at. So the hard disk makes it. There's a DAP. This is a structure in memory that has a block address, 64-bit block address, and a count of blocks. And mine when I install. When you write the files to the hard disk, that's when you set the absolute address of the kernel. So it's every time you update the kernel.bin, you have to update the boot sector. Every time you make a new kernel, you have to update the boot sector. Okay, that's how it works. The CD-ROM, it's kind of easier, more predictable. But anyway. So I have a file find. This will get the cluster number of a file. If you want the cluster number of a file so that you can write, then okay, I'm trying for minimum line count. Okay, so my kernel navigates the FAT32 file system, right? My kernel has to navigate the FAT32. Why on earth would I put navigating the FAT into the hard disk? That's stupid. The bootloader. Why would I put navigating the FAT into the bootloader? When I install, I just use my existing navigate the FAT, and then I just write an absolute address, and I store it contiguous. I store my kernel contiguous. So this is the minimum line count. If I duplicated all these lines of code, my line count would go up, wouldn't it? That's just dumb. So in my install routine, when you make the operating system, when you make OS partition boot install, that makes there's only two files. It's kind of a joke. There's compiler and kernel. So it compiles the compiler and kernel, and then it writes into the installs into the boot sector. It sets the DAP block address. It calls file find, like I told you, and it gets the cluster, converts the cluster to a block, and then writes the boot sector. So I was going to say something. Okay, so the kernel.bin, the kernel, when you compile the kernel, this is the make file. It's a joke. It's just including code. We don't have a make file. It's that fast. It can compile everything in half a second. So you don't even need a make. You don't need object files. I'm limiting it to 100,000. It's always going to be small because I'm limiting it. Anyway, so the kernel make file it goes in the order of this file. So kstart is the first. I forgot to tell what the bootloaders do. So the bootloader identifies where it's located, and it copies itself up to the 90,000s, and then it uses the already absolute address of the kernel, absolute address of the kernel.bin. It loads it one block at a time, and then it jumps to boot RAM base. This jumps back down to 7C. So it loads back into 7C after it's moved itself up to the 90,000s, and then it jumps to the start of the kernel. And the kernel bin starts with the header, and then it's the kernel start. So this is now what. Okay, class, we're in real mode. Did you realize that? I'm not doing UEFI. They're gonna support me. I'm not supporting them. They use ELF and they use graphics file formats. It's totally fucked up for me. So I'm just gonna command everybody that from now on you can only reduce God's temple, not line count. So this is called in real mode by the bootloader. It skips it has some data structures here. The GDT, you guys love that, don't you? Ooh, do you know what a GDT is? Ooh, I did that in 93, folks. Anyway, you guys are not using 16-bit. A 16-bit has twice as wide of entries, and guess what? I have to pass through. I start in real mode, and I change to protected and then to long. So I start in real mode, then I change to protected, and then I change to long. But I do a trick. I skip every other entry so that it works for both protected mode and long mode. So in other words, I use the same GDT for protected and long mode because they're bigger. Everything's bigger in long mode, except the TSS. That's kind of all different. Anyway, the TSS no longer holds the registers. You don't have a push all. So when my kernel boots, this is real mode. It calls interrupt 10 to change to VGA, to change to 640. It calls memory E820 to get the memory map. This is still in real mode. My kernel has been loaded and it's still running in real mode. I made my assembler be able to do 64-bit, 32-bit, and 16, but my compiler only does 64-bit. Did you know it's easier to do a 64-bit compiler because you have more registers? It's much harder to do a 16-bit compiler because you have fewer registers and you have segmentation. My assembler does not do segmentation. It only does limited 16-bit. So now we enable E820. I don't. Brendan at OS Dev gets really carried away. Mine only works in 64-bit computers, so I don't have to worry about all the weird ones. So here's where I set up my my GDT. This is what a person was asking about. There's the limit of the data segment, limit of the code segment. In long mode, the limit doesn't matter. The base is 0 for DS and CS. The only segments that are functional in long mode are FS and GS, and those you have to change with the model specific register. Actually, I'm not too sure. I think you might have to set these up. I don't remember, but you can't change them. They're locked on 0. Then you make a pointer to your GDT, and then you load your GDT. Then you change your CR0, and this, my friends, is this. Okay, then we jump to 32-bit. Now when I do a fast reboot, I don't go all the way back to real mode. I have a fast reboot that just refreshes my structures. So this is 32-bit. So we're doing some stuff. I have my compiler has a table of absolute addresses in the code that have to be patched. So my code has to be patched. All the addresses have to have 7C added to them. So while we're still in assembly, before we're doing the C code, we go through the table and we patch all those addresses. I have all the symbols. You were wondering how I had my symbols. Well, anyway, now we set up the heap. We have to have that set up. Oh, we have to initialize memory to identity map. I can't do that in C because I only have a 64-bit compiler, so I have to do this in assembly. So I initialize it to identity map. Guess what? I map it with 2 meg blocks instead of 4K. You can use either 2 meg or 4K, and I use 2 meg, except for the first block because I have VGA. There's initializes the floating point unit, saves a copy so that we can have a standard. Then it initializes my CPU structure. Where did we call? We switched to 64-bit mode. I went ahead and made that a subroutine. This is where you switch to 64-bit mode. You set up. I don't know what that is. I don't remember what it is. My assembler has funky. I didn't make. I do limited support for those instructions to save me effort. You don't need to anyway. So I load the page table into CR3. This is where you change write model specific. This sets it to 64-bit. Enable paging. I have to enable paging for 64-bit. I don't know if that technically. I think it happens when you do this. When you do the jump to a 64-bit code segment. And when you restart the kernel, I can do a fast reboot. Anyway, the last thing we do after we change to 64-bit. I made a run level flag that you might want to investigate to see all my different. Every time I make an accomplishment, I set a bit in a run level. Okay, if we're in 16-bit, we set a bit, 32-bit. If it's been patched, if the absolute addresses have been patched, if we've changed to 64-bit, if we initialize the boot heap, if we initialize the full heap, if we initialize raw VGA graphics, if we got interrupts up and running, my IDT, if we got multiprocessing going, if we got the disk going, if we got the compiler going, if we got the window document manager going, if the window manager, if we've logged in, if we did the registry, and then if we finished Atom 2 directory, and then if it's parked in, Atom goes into the Atom task is what is calling all this stuff. And at the end, it goes into Atom, and the very last thing before these subroutines is it jumps to kernel main. So it sets up FS, jumps to kernel main. Kernel main is in CK end. So this is just now we're in 64-bit C code. So we initialize the rest of the heap. We set up the timers, the interrupts, calibrate the time, set up the keyboard, mouse, initialize block devices. Then we load the compiler, and then we start compiling Atom 1. This is like autoexec.bat. So we compile my header files that declare all my headers for the kernel, and so these are where the header files are. And then when it's done, it goes into the Atom 2 directory. Remember I told you it's the Atom gets just-in-time compiled. So Atom 2 includes a bunch of files. This is 40,000 lines that get compiled every boot. So it sets up the disk, sets up the window manager, WordStat, a bunch of stuff. Then when it's done, it goes into your account. Atom 3 is in your account directory, and that's where the rest of the files. And then when it's done, Atom goes into the Atom task goes into a server state where you can tell him commands like print hi. Now Atom just printed hi. He's serving. You can tell him to include code, and that's like kernel memory. That'll be system-wide. Everyone gets it, and it never dies. So if you make a wallpaper, you want that kernel memory. So you Atom include your wallpaper. So anyway.